So this particular lecture is on big O notation. And big O notation is a fancy way of, it's basically just like how fast your algorithm is going to run. So the formal description of it is like how fast your function runs relative to the size of the input that you pass in. So let's take a look at this quick YouTube video right over here. Let me copy that. Open link and incognito. I'm going to turn off.
It's not that easy.
Oh my gosh. Okay. All right. All right, so what we've got here is a bunch of sorting algorithms here on the board. Now, each sorting algorithm is basically saying, I have a bunch of things that are varying in terms of size. You can see all the way on the left of each one of these is the smallest input, and then you go all the way up to the right over here, and that has the longest bar. And you wanted to make it look like a linear graph going up, like a half of a triangle, or I guess a right triangle. Now you'll also see that there are multiple different types of sorts that we're using. So there's selection sort, shell sort, insertion sort, heap sort, quick sort, merge sort, and so on and so forth. The ones that we've known so far are the bubble sort. Remember we did the bubble one where we compare each one right next to each other, we go all the way through, and then we just do it again and again until we're all the way to the end. And what you'll notice here is that bubble sort takes a lot longer than every other sort. In fact, every other sort has already finished. It's going to take bubble sort like another 5 or 10 seconds to finish. And you have to ask yourself, why? Like, why is this happening? If I go again to this other one, let's go to the very beginning. Okay, so we've got a whole bunch of, unsorted things, and quick sort's already finished, and the rest of the selections are going to go through in the back to try to sort this. The idea here, the reason why I'm showing this particular video is that I want you to see just like the speed of different types of algorithms. Certain ones like quicksort are really fast, and bubble sort is really, really slow. I'm not going to bore you with the rest of this video, but big O notation let's put it this way. So I'll just read this and I'll tell you what I actually think of it. So big O notation, the formal definition is the complexity of your function, that's the O, in terms of input size, which is the N. Now, big O notation is really, really big in interviews. And it's also really, really big if you're working at a huge, huge company. We're talking about like Amazon size. Because any code that you write that's not performant, at the scale that they're at, could wipe them out. It's really that important. So they're really focused on speed. They're really focused on how efficient your algorithm is. But for most companies, like there was one person that I talked to who used to work for Blizzard Games, and he says, we never cared about the complexity of our code. And they care about frames per second. So if you're scrolling around, you're like turning your character really fast in like a first-person shooter, they have to make their code fast enough so that like the frames per second is so fast that it looks like you're actually turning in real time. And they said, we never had to worry about big O notation. So there's 2 times that you're really going to need to worry about it. One of them is for interviews, and you want to wow your interviewers. And number 2 is if you're working for a huge company, Google, Microsoft, Amazon, and things like that. So these are the rankings of most of the common big O notations. You got O of 1, O of log of n, O of n, O of n squared. The big 3 that you need to memorize are O of 1, O of n, and O of n squared. I'll go over what each one of those looks like with actual examples. So O of 1, remember the O is the complexity of your function relative to your input size, which is the n. O of 1 is known as constant time. So regardless of whatever you pass into your algorithm, it's going to take a constant amount of time to actually run. So let's take a look at this code right here. We've got a def first element is red, and you pass in an array of stuff. And it's just return true if the first thing in the array is red, otherwise return false. No matter what you pass in, it could be an array of 1 item, 10 items, 100 million items, it doesn't matter, because I'm just looking at the very first one. I don't care how long this array is, it's just going to be a constant amount of time. Now, the real life example of this is that there was a country in Africa that recently received internet access. Now, they said the internet access was so slow that they could have a carrier pigeon carry the information to a town 50 miles away faster than you can send it via the internet. So that's what they did. They set up a real race. They were trying to upload something to a town in about 50 miles away. And then the pigeon had a USB drive with all that same information, and it flew 50 miles. And obviously, because I'm telling you the story, you know the result. The pigeon won. Like, the pigeon won compared to the internet speeds of that particular African country. But does anyone have, like, how do you, like, so that's an example of O of 1 time. Does anyone know why? If you had a guess.
So the internet speed is variable in, I guess, in that example, but the pigeon has a pretty much constant time because it's 50 miles away. It's going to go fly straight to its destination. The internet speed could experience problems along the way. Why? Maybe, I'm assuming why that's the problem, or maybe whatever their internet problem was. But a pigeon is going to make it there in constant time. That's a big takeaway from that.
Yep. Yeah, that's pretty much right. So the internet thing is it can't be measured. Like, it's fun to write inside of a newspaper and to have that kind of a race, but it can't be. It's not the same thing. When you upload something that's like 1 kilobyte, it'll definitely get there faster than the pigeon. But if you're uploading something that's 100 gigabytes, it's going to take a lot longer than the pigeon's going to take to get there. But the pigeon is O of 1 because it's just a USB drive. It's a fixed amount of weight, and you can put 1 gig on there, you can put 10 gigs, you can put 15 gigs worth of stuff inside that USB drive, and it doesn't affect the output. The pigeon is still going to take the exact same amount of time to fly there because the weight of the USB is exactly the same. So the first one that you will need to know for your interviews is going to be O of 1, which is constant time. So, like, some real life examples, if you wanted to look up the 6th element in an array, that's going to be constant time because you know exactly which one you're looking at. If you're looking up something in a dictionary with the key value pairs, as long as you know the key, it's constant time lookup because you know it doesn't matter based off of the input. You already know exactly where it's located. It's like saying, let's say that you are, let's say you want to SWAT someone's house. So let's say you want to SWAT somebody's house. If you know the exact address, you can just provide that to the police, and then they will be able to SWAT that house in O of 1 time because they know exactly where it's located. Versus if you were doing something of O of n time, it's basically, oh, hey, police, I know that the person that I want to SWAT is somewhere on this street. They're going to start at the first house and go out into every single house, and it's going to take them a linear amount of time based off the number of houses that there are. That's the second one that we need to know, which is O of n, linear time. What this means is that it's going to grow, the amount of time that it takes something to run will grow linearly based off of what you pass in. So we've got this very simple method, does it contain it, which is basically linear search. I've got an array and a value that I'm looking for. So I'm looking for this needle inside of this haystack. I've got a pretty easy for loop. For item in array, if the item is equal to the value, return true, otherwise return false. So I'm iterating over every single thing inside the array until I find the value. So it's like swatting. I'm going to, if I had like a street of 100 houses and you didn't know where that person that you wanted to SWAT lived, you have to go through 100 houses to find that person. Now, you could find it at 50, you could find it at 60, but you're talking about the worst case scenario when it comes to big O notation. You could reach the 100th house and then you find the person. Or you can reach the 100th house and that person's not even on that street. Versus linear time is much better. It's like, hello, they're located at 125 South Clark on the 17th floor. You know, okay, we know exactly where they are. We'll get there much faster than trying to find, like, brute force every single one of them. Another real life example, generally speaking, if you have more money, you have more problems to worry about. The third one that you'll definitely need to memorize is O of n squared. Now, this is basically whenever you see O of n squared, it's a loop within a loop. That's what's going to happen 100% of the time. So it's going to be a loop within a loop. So let's say that I want to find all combinations, and I have an array of numbers. Let's say 1, 2, 3, 4, 5, and I want to create all the combinations. It'd be 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 2, 2 and 3, 2 and 4, 2 and 5. So I do that. If you counted it all up, I think it's 25 of them. And you'll notice that 5 squared is going to be 25. So I've got all combinations. I've got an array. Let's say there are 3 things inside of there. I've got the results. I'm going to iterate over the array once, but within it, I'm going to iterate over it again. So this is when I see that loop within a loop. So stock picker is very popular for this one. Sum pairs, the algorithm is very popular for this one. And I'm just appending the first number with the second number. So if I were just doing 1, 2, 3, the first time through, number 1 is number 1. And number 2 is also equal to 1. So it'd be 1, 1. Then this one iterates again. 1, 2. Iterates again. 1, 3. And then I move on to the second number. 2, 1, 2, 2, 2, 3. By the end, you're going to have nine things based off of your array that was originally the size of 3. So 3 squared gives you that 9. Constant time, O of 1. Linear time, it's going to grow based off of if you want to iterate over something 5 times, it's going to take a short amount of time. But if you need to iterate 1,000,000 times, it'll take 1,000,000 times that. And then n squared is going to be that quadratic time. So based on the input, the amount of time that it takes to run is going to double. Some key takeaways that I'd want you to look through is that when we search through hashes, it's much faster than searching through arrays. Arrays, by definition, keep track of index. So insertion into an array is really, really fast because you just throw. Insertion into an array is really, really slow because you have to find the last thing and then add a new one onto the end. And if you want to look for something in an array, you basically have to linearly look through the entire array. If you're doing a hash, you can just basically say, I'm going to pass in the key, and then I'll automatically get the value. So let's try this real quick. I'm going to jump back to week number 1. We're going to just take a look at a few people's challenges, and we'll see if we can figure out the big O notation. Let's choose this day and maybe the 9th. All right, let's take a look at factorial, maybe linear search, Roman numerals. We'll just start with that. So we're going to go to factorial. I'll open just these few for now. The fun part about going back to week 1 is you'll see how bad the code was. Okay, this is hard to read, but let's take a look. So factorial. So you're using a recursive call here. Let's see something that's not using a recursive call.
I just did a one-liner on that one.
Yep. Let's take a look at Juan's one. Everyone memorized the factorial one. So factorial, anytime that you use a recursive, it's actually 2 to the n. So it takes a lot long. It's probably the longest one to run compared to all other inputs. So whenever you see a recursive call, it's generally 2 to the n. Let's see if I can find something else. So linear search, let's just take a look at Christina's answer here.
You're saying it's 2 to the n by memory or space? Or sorry, speed or space?
So that's going to be by time, not by space. Space complexity is something different.
Really?
Space complexity is different from big O notation, and I guess it's similar. It's similar in terms of measurement.
Yeah.
Space complexity is how many new variables are you using, and how much memory is your program using. Versus this one is how long does it take to execute.
Yeah, I was just curious because recursively you're saying it was speed-wise it was that slow. I was like, oh.
Speed-wise, it's 2 to the n.
Yeah. Wow.
All right, so let's take a look at this one. So we've got a linear search, and the way that I'm reading through this is you're looking for a value, and you've got an array of things to look through. I'm going to disconnect this because otherwise.
Call from
Okay. All right, so I've got a linear search. I've got a value that I'm looking for and an array to search through. So I've got a single for loop over here. When I generally have a single for loop, what is the big O notation of it?
O of n. O of n.
O of n. Why?
Linear. You iterate.
Yep.
Well, is is it not because the maximum possible value times of iteration is n? So whatever the size of that is, it could be the very last thing.
Yep, or it could not exist at all. That's the worst case scenario. So yes, it is O of n. Whenever you have a one single loop, that's going to be O of n. And the reason behind that is you have to look through every single, like if you're looking for a needle inside of a haystack, you have to look through every single index of that array. So let's say the array is n digits long, like n of n length. You have to look through that n times in order to reach the end. And then if you find it, you'll return it. If you don't find it, then you've just wasted a bunch of time. But yes, every time that you have a single for loop, it's going to be O of n. Let's take a look at Roman numerals here. I'm going to pick on Christina again because she's on the very top. All right. So let's take a look at this one. This particular code over here has a bunch of things inside of there. So let's take a look at this. Just lines 10 through 12. We've got a single for loop, which means it's, don't all speak at once. Yep, it's O of n, because I've got a single for loop. I have to iterate over every single thing. So I know that this is going to be O of n time. Same thing here. I've got a for loop, and I've got an if statement over here. The if barely changes anything. It's just a quick check. So worst case scenario, I'm looking at this. If it goes all the way through, it's going to be n of n length. So I'm going to do O of n again. Let's take a look down over here. So I've got a for loop and then another for loop.
A little bit. Sorry to interrupt.
Sure.
There you go.
Sure. So I've got a for loop within another for loop. What is the big O notation whenever you have a loop within a loop?
Quadratic time.
It's going to be quadratic time. And why is it quadratic time?
Because a square, two for loops is going to take that many possible iterations to do it. When
Yep.
Squares.
That's pretty much it. So right now we're going to iterate through this pieces.length time. I don't know how long that is, but within there, I'm going to also iterate from 1 to 9 every single time that I iterate through pieces.length. So let's say pieces.length is 3, and this one is, I'm running through this 9 times. So I would have to do this, I don't even know what that one is. Like the input is, yeah, so I have to iterate through this 9 times 27 times, if I'm not mistaken, in order to make this one work. So it is this would be an O of n squared. Anything else over here?
Okay, so if you wanted to give one label to that entire thing, would you just use the highest?
Good question. Good question. Let's actually bring that one back. So right now, it's like, it's not purely O of n squared because you have a fixed number inside of here. But on the worst case scenario, let's say if it was, the worst case scenario would be O of n squared. If you have n and it's equal to like 10, 10 squared will give you 100. But if I added another 10 on top of it, it doesn't really, it matters on the smaller ones, but it matters very little on the upper ones. So if you have something that's, 5,000 things long and I square that, it's going to take a certain amount of time to run. But if I add another 5,000 or 5,000 divided by 2 or 5,000 divided by 5, it doesn't matter. So you always take the largest thing that shows up. So you drop the coefficient, which is probably more than I want people to know right now. You drop the coefficient or to get rid of all the constants. Yep.
Also, I saw a piece of blocks you went through in this particular person's code.
Mm-hmm.
Is it not also some asymptotic notation also affected by the methods and functions they use within those control structures? I think you're talking about like nested for loops, but isn't like insertion and stuff in between those blocks also affecting the notation?
Technically speaking, yes. So the answer to your question is yes. That's more than I want to get into. Whenever you do something dot append, it is actually O of n time because you have to find the last thing in the array and then insert it. And then it could be O of n in terms of space as well because you have to get a new array every single time that you go over the certain length. But yeah, for the sake of just learning Big O at a very basic level, and we're going to add on to it later, short answer is yes. Where did all my stuff go? Okay, they'll disappear. Are there any questions on Big O that I can answer off the bat? Okay. While we're waiting for this to load, let's go over a few additional methods that I didn't get a chance to get to yesterday.